Hi, everyone. My name is Matt Stevenson. I'll be presenting with Jamie Dunckley on the eRoadMAP, which was designed to help map the future of the electrification of transportation. And I want to thank Kristen for her talk because it could not have teed us up any better for what you're about to see. First, though, I have to show this wall of logos because this project could not have been built without all of the support, participation, and collaboration of all of the project partners that you see here. There are a couple of entities you might notice on the wall of logos here. A small local company called Amazon. Seattle City Light was one of the project partners, and lots of data collaborators that contributed the information that you're about to see. So this is the project team. Jamie was the ringleader of this motley crew. She is our project manager at EPRI, the Electric Power Research Institute. Her colleague Jeremiah is an electrical engineer who helped us with some of the really gnarly nitty-gritty electrical stuff, thank goodness. I was leading up the CORE GIS team, which consisted of myself, Eldon Goldenberg, and Melinda Minch, who are an incredible husband and wife team based out of Victoria. And not coincidentally, Eldon did a lot of the data work on the maps that you just saw, that Kristen presented. And more than once, we were fighting over his time. Okay, so here's what we're going to talk about. We are going to explain why we would build something like eRoadMAP, like what's the purpose of this thing, and what we considered our task to be and who the intended audience was. I will talk about the open source tech that we used to build it. We had some design guidelines which were extremely helpful in designing it in a user-friendly way. We're going to talk about the challenges. And then Jamie is going to step us through the outcome. And if time allows, we'll have some discussion and question and answers.
So I put this map in just to kind of tee up the conversation a little bit. Again, thank you so much for the presentation beforehand. But my job is thinking about the electrification of transportation and how I can make sure that all utilities in the US, there are over 3,000 utilities in the US, are ready. And what I mean by that is that as vehicles are electrified, they're going to be needing to plug in somewhere. And often that comes at a faster rate than what utilities are used to. So it's really kind of figuring out how that happens. So this is just an example where I drew a lasso around the city of Charlotte, and I tracked all of the medium and heavy duty vehicles that went into that city over a week, and then I tracked them. This isn't the full data set, this is just a part of it, but what I'm trying to get across here is that if the city of Charlotte decided to electrify, and there are electric trucks that are going through there, but also going elsewhere, here is the impact. So we really have to think about how kind of even localization, most of the adoption right now for larger vehicles is happening in California, but that spreads out very quickly elsewhere. And so they need the infrastructure, right time, right place, right power to be able to enable it. Okay, so this is kind of giving us some motivations here. Utilities have been in this space for a long time. We don't often see it, but they are there. You turn on your light switch, they know how to do that. Electric vehicles are different than a lot of the loads they've dealt with before, mainly because they move. They are not a heat pump. So when you think about the when, where, and how much electric vehicles are going to charge, they may be charging at home. They may be charging en route. You might decide, oh, I'm going to get this electric car because my employer has free charging. So wherever it might happen, that's where you have to be ready. And then people are just different. Seattle actually has a really low average VMT compared to everywhere else. And so figuring out how those local dynamics change the amount of power you might need, it's not a heat pump, right? The second bullet there is that there isn't one data set that captures it. If I could have purchased that data set, I would have purchased it. But we actually don't even have a good data set that documents how conventional vehicles drive. We have some surveys out there, but there isn't one data set that has it, partially because there's some PII information in there. You know, folks don't want you to know exactly where they go at all times. It's a little creepy. So we had to pull together a lot of different data sets, some with kind of logistics, telematics companies, registration data, a number of different things we had to pull together. We were banging on Amazon's door. Where are you going to electrify? How many trucks do you have? How far are they going each day? We're talking with garbage truck drivers. How far are you going? How many vehicles are you going to purchase? So pulling that all together. And kind of where that leads is, well, I guess I'll start with the first one there. EV loads can be big. So here's another conundrum with this whole process. Utility companies are good at this. This is their job. But if Amazon, this is a example I often give, decides to purchase 500 Rivian vans and bring them to one of their warehouse deliveries. They can do that in 6 months. That amount of load is like a small neighborhood, right? And so utilities usually have a lot of time through permitting, house building, all of this stuff to bring power to that site, not 6 months. So what this map does, or what this kind of analysis that we'll get to does, is bring confidence that the loads are coming so the utilities can start planning sooner than they would usually do. So to plan effectively, we need to know where, when, and how much. So the task here, we need to create a tool that enables utilities, fleets, companies, and others to make data-driven decisions about where to place resources, make investments, and efficiently use existing infrastructure. We actually have 21 hosting capacity maps on our website. It's not complete, but we are trying to work to show where there is available energy and power so folks can go there without needing a big upgrade. You can go.
Sure. Okay. Yeah. All right, so not only do we want to make that data available, but we wanted it to be available at multiple scales to show regional variability and granularity, which is something that I'll come back to again and again. We wanted to be able to animate the time series of forecasted energy demand and then provide a range of additional supporting information through pop-ups. We had to build an infrastructure to enable frequent updates because, as Jamie alluded to, this is all in flux because companies are making decisions and individuals are making decisions. And as I mentioned, those additional reference layers, including the utility service areas, the distribution lines, and existing substation capacity, all needed to be hosted and served onto a single map from multiple sources. And then finally, we wanted to allow users to filter the minimum and maximum megawatt hours per day of their particular project or their interests. And as Jamie mentioned, the audience are utilities, their boards, commissions, all of the decision makers, the regulators, transportation companies, anyone who needs to make a big ticket decision that is going to be influenced by the availability of electricity. Okay, so how did we build this? It's mostly open source, but EPRI is a proprietary shop, so you're going to see a little bit of Frankensteining going on as I step through this. The data was delivered to us in ginormous CSVs with millions of data points showing kilowatt hours within H3 hex levels 5 through 8. I'll unpack what that is in a subsequent slide. The vector tile server was all open source. It was Postgres plus PostGIS plus PG tileserve from 3 entities that all like blue logos. The base map was constructed and customized using Mapbox, the GLJS API, including turning off the state label for Kansas. Ask me later why we did that. The website itself was built with HTML, CSS, and JavaScript. I built the first version of this, but I'm not a web developer, which is why Melinda's on the project now. And she can do things with Python and Golang and all sorts of stuff that I don't really know. And then the infrastructure itself is the most Frankenstein-y part. As I said, Mapbox was our base map provider, but we were also hosting some vector tiles there. Our CORE GIS team did all of our testing and idea iteration in GitHub, and then we had a dev and a prod instance on Azure, and all of that was accessed through Citrix. Okay, now for the pretty part, the finger painting. We had these wonderful brainstorming sessions with the EPRI in-house graphic designer and her contractor, Michael, to come up with a pretty robust set of colors, fonts, logos, and guidelines for how all of this should be used across the web map and all of the supporting documentation that's accessible through the website. As I mentioned, we used Uber's Hexagonal Hierarchical Spatial Index, or H3. This is a global network of buckets that are intended to help solve the modifiable aerial unit problem. They work pretty well. They're not perfect, but again, there were millions of these things, so that was one of the big data wrangling challenges we faced. All right, so those are all the pieces and components, and we used it to build this. This is a screenshot of eRoadMAP. This is the default view that you see when you open it. And what this is showing is forecasted near-term electrification needs to the year 2030. So that red box there tells you where you are in time, while the map is showing you where you are in space. You can animate this backwards and forwards through time. As I mentioned, you can also filter the minimum and maximum megawatt hours per day that you want to show on the map. And there's a bunch of other stuff that we're going to look at. The thing that I like the most about this map is that you can take it to full electrification. There's no date associated with when this will happen, but that's a lot of energy demand. That's a lot of people using electricity for their transportation needs. But energy isn't the whole story. There's also power. And we used some visual cues to let people know if they were looking at energy, mostly yellow, or power, mostly blue. Similarly, you can go from 2030 to full electrification. Again, pretty stark difference. What's interesting about the power representation of full electrification is you can really see these linear transportation networks. It turns out, as Jamie mentioned, these trucks use a lot of power. And if you are a utility planner and you want to remove them from the mix, that's possible down here with this cute little green truck icon. You click that little button and the transportation networks disappear. So there are a lot of ways to modify what you're seeing based upon your particular use case. This is one of the layers that I've been working to update. This is the map of all 3,000 plus utility service providers. I had no idea before I worked on this project that there were this many. It's truly astonishing. Okay, I also have to mention that we are fully aware that you were basically just looking at maps of population density. And as usual, there's a perfectly appropriate XKCD cartoon that has an inappropriate reference on it. But yes, kind of sort of we're looking at population density because people need power and you have the most power where there are the most people. So the key to making this useful is that granularity and regional local variability that I was talking about earlier. Jamie's gonna illustrate that with a few examples.
Yeah, so just to show you a bit, as we use this map, I often am showing folks how to use it. So this is just an example of one area in Philadelphia going from 2026, 2030, and full electrification. Again, as Matt said, full electrification, there's no year attached, and there's going to be other technologies in the mix. But as utilities plan, it is helpful for them to think about what that far end goalpost is if we're going to get there. So this is just an example in 2026. You can click on that hexagon there, and it pulls up the utility that serves that area, the energy needs per day, whether it's light duty, so stuff we drive, or medium and heavy duty. It also shows peak power and whether that power is managed or unmanaged. We can talk about that later if you want. And then actually when you see those dark hexagons, if you turn on the satellite data and zoom in 100% of the time, you see what is causing that. And in this case, it's an Amazon distribution facility, a trolley depot, and then you see all the other stuff there. So it's a really nice way to pull together the demands of co-located companies, which utilities don't often have on their radar. So they know what their big customers are. These customers may be new big customers, and then where are they co-located with other customers, because it might mean that they have to upgrade a substation. And then the same thing as you go full electrification, you see other hexagons pop up or getting dark. And in this case, the really darkness is around an airport and the loads associated with rental car facilities, because really their objective is to turn over as fast as they can so they get those cars in and out within a couple hours and they need to charge them. So that's the big peak there, but you see enterprise budget. So we're working directly with some of those to kind of get their estimates of when they're going to electrify and how many cars they have. I'll start this. Okay. I'll start this one. We went back and forth about what we were kind of allowed to put on these slides. So EPRI, I've been working there for 11 years. We handle nuclear stuff. And so we are and any nuclear company in the US is required to be part of EPRI. They have to purchase EPRI membership just to make sure everything's safe. So we are really good at keeping safe, really technical nuclear reports. That does not lend itself well to a public, dynamic, user-friendly website. So we've had to work through a lot of security and every time I do an update on this, are you sure it's public? It's like, yes, please, it's public. So anyway, read between the lines there. Happy to talk later. There you go.
Okay, and then the technical challenges. And the reason that we showed a pancake is one of the IT managers referred to our project as the first pancake, which if you've ever made pancakes, the first one is usually misshapen and kind of burned. So the technical...
It's like the fifth pancake now.
Yeah, we're on phase 5, so our pancakes are perfect, yeah. So the technical challenges are that we had every type of spatial data. We had lines, squares, hexes, points, rasters, times energy, times power across 3,000 utilities with no common schemas. And sometimes the grid capacity would be given to us in incompatible pre-aggregations with breakpoints that didn't match the other pre-aggregations we received. Anyway, thankfully, Eldon and Jeremiah handle most of that. The IT stuff, this is the Frankenstein problem. It's open source plus proprietary plus a large organization, which results in lengthy and complicated SQA processes. But they're getting faster. And administrative can be a total nightmare. Substations in particular are very, very sensitive. Even though you can see them on Google Earth, sometimes the utilities are a little squirrely about releasing it to you. And now Jamie's going to finish it up with the outcomes.
I know we have like 2 minutes left.
You got it.
Okay. So utilities are now using these hexagons, energy and power, to plan for their distribution and planning moving forward. So that's great to see. This is really important, as I said, 100% electrification is in there, not because I know exactly when that's going to happen, but building once is much more effective than a customer asks, you build for them, then the customer next door, you build for them, and goes like that. Like, it's better to do it once, get everybody served in a more timely way. So, and also it means that we are planning in places where we're confident that infrastructure needs to go, because utilities can't waste money from you and me. Knowing where there's available capacity on the grid and using those areas first rather than building some infrastructure somewhere else is really important. So that's why we've been looking at hosting capacity. This allows electrons to be sold without upgrades, and that helps with downward pressure on rates. So you use existing infrastructure to sell more, which means you and I pay less. That's it. Okay. There's lots of other layers on there to play with, the website's there.
Yeah, I think we could do 1 or 2 questions if anybody has any.
Amazon is also building data centers. Can you give a sense to the scale, and are there similar or different challenges involved with that?
Yeah, great question. I'm battling this internally. Yes, data centers are sucking up all the air right now, and rightfully so. They are huge loads. What we see is that electrification over time, data centers are going to be bigger and faster first, but in the long run, actually, the electrification of transportation is bigger overall. I will say, though, that transportation electrification is on the distribution level. So, again, so happy we had that presentation first, kind of the smaller level. Data centers are on transmission level. So within a utility, that's actually a totally different group. They're all connected, but it's a bigger question. But yeah, great question.
And then there's one more in front.
That's the same question.
Okay, perfect. Okay.
Data centers comes up here too.